Hi everyone, my name is Johannes Ernst and I'm going to talk about our paper Private Stream Aggregation with Labels in the Standard Model. This is joint work with Alexander Koch. Okay, imagine a scenario in which every household has a smart meter installed and the smart meter is capable of sending the current power consumption to the power supplier in regular intervals such as every 15 minutes. The power supplier is interested in these data, for example, to be able to perform better load prediction and load balancing in their networks. However, these data are clearly privacy sensitive because from the variation in the power consumption, one can easily guess the work schedule of the people living in the household or whether they are on holiday or not. And for the power supplier, it is often sufficient to know the total power consumption of all their clients in a certain street or in a certain area. And this is where private stream aggregation comes in. In private stream aggregation, we have several clients. In our example, these 3 laptops and 1 server or aggregator. Then we have a trusted party who in the beginning performs the setup, that is, they give the secret key to each party and the aggregator. Then at each time step, the clients take the current power consumption, encrypt it and send it to the aggregator. The aggregator cannot read the individual values because they are encrypted, but the aggregator has an aggregate decrypt function which takes as input its secret key and the 3 ciphertexts of the clients. It then outputs the sum of the plaintext values. So then in the next time step, the clients again would encrypt their current power consumption and send it to the aggregator. The aggregator would compute the sum, which is this time 6. And now what happens if the power supplier exchanges the red ciphertext of the first party by the blue ciphertext of the first party? Well, the sum increases by 3, whereby the aggregator knows that the blue plaintext value of the first client is greater by 3 than the red plaintext value. And thereby the aggregator has learned information about individual values of the first client, but this was the thing that we tried to avoid in the first place. So an important property that private stream aggregation schemes should have is that they support the use of so-called labels. And in practice, labels can be an integer or a string, and in our example here, they are colors. And the labels ensure that you can only input ciphertexts to the aggregate decrypt function which were created with the same label, that is in our case the same color. And this then prevents mixing the blue and red ciphertexts and prevents this quiet attack as long as every client only encrypts 1 message per label. Okay, a bit more formally, private stream aggregation consists of 3 algorithms. The first one is the setup algorithm, which is executed by the trusted party in the beginning, and it outputs public parameters, which you can think of as the specification of the mathematical group in which all the computations take place in, and then secret key for the aggregator and 1 secret key for each client. The encryption algorithm takes as input the secret key of the client, the current label and the current plaintext value of the client and produces a ciphertext which is then supposed to be sent to the aggregator. The aggregator, upon receiving ciphertext from all clients, inputs these ciphertexts together with the current label and their own secret key to the aggregate decrypt function in order to obtain the sum of all the plaintext values. Now, private stream aggregation has a security notion called aggregator obliviousness, and this is meant to capture the intuition that if an adversary does not corrupt the aggregator, then the adversary should learn nothing about the plaintext values of the uncorrupted clients, and if the adversary corrupts the aggregator, then the adversary should learn only as much as the aggregator learns, and this is the sum of the plaintext values of the uncorrupted clients. This is formalized by an indistinguishability-based game between a challenger and an adversary, and the adversary can ask encryption queries at any point in the game, where they specify a client, a label, and a plaintext message, and get back the corresponding ciphertext. Furthermore, they can corrupt parties, so they can corrupt clients and the aggregator, and get the corresponding party's secret key. And also corruption queries can be asked at any point in the game, and therefore we say that corruptions are adaptive as opposed to static. Then, at one point during the game, the adversary can ask a challenge query where they specify a set of uncorrupted users, and for each of these users a left message and a right message. And the challenger then tosses a coin and decides whether to encrypt all the left messages or all the right messages. Now we have two conditions for the adversary. The first one says that if the adversary has corrupted the aggregator, then the sum of all the left challenged messages must be the same as the sum of all the right challenged messages, and this is to prevent that the adversary uses the aggregate decrypt function to trivially win the game. The second condition is one that is shared by many PSA schemes, including ours, that for security we restrict the adversary to get only one message per label and client. This is good from a security perspective to avoid this leakage that I explained with the red and the blue ciphertexts, and it is also easy to enforce in practice by programming the clients to use a new label for every new message. Okay, so what did we do in this paper? We propose a private stream aggregation scheme with labels that is secure in the standard model and based on key homomorphic pseudorandom functions as the only primitive. We use proof techniques from a paper by Abdallah and others, and our scheme is similar to a PSA scheme of Valovich. However, the resulting schemes have quite different properties. Previous PSA schemes usually were either only secure in the random oracle model, or did not support labels, or were only secure under static corruptions, and with our scheme we fill this gap. However, a concurrent work of Waldner and others also roughly achieves the same properties as our scheme. We implemented our scheme based on a lattice-based key homomorphic pseudorandom function, which is secure in the random oracle model, and therefore also our concrete implementation is only secure in the random oracle model. Furthermore, we did performance evaluations and compare the running time of our scheme to previous PSA schemes and to the work of Waldner and others. And we describe how to use existing techniques to achieve a decentralized setup and thereby get rid of the need for a trusted party. And we explain how to use techniques by Chan and others to get fault tolerance, that is, allow decryption even in the case that some clients fail to submit valid ciphertexts. Okay, in order to explain our scheme, I first have to explain key homomorphic pseudorandom functions. And I start with normal pseudorandom functions. So a pseudorandom function is indexed by a key k and maps from an input space z to an output space y. And when the key is chosen uniformly random from the key space, then the pseudorandom function should be computationally indistinguishable from the random function. A key homomorphic pseudorandom function has the additional property that the key space and the output space are mathematical groups, and that the pseudorandom function is a homomorphism between the key space and the output space. Concretely, this means that for any input z and any two keys, it doesn't matter whether we first evaluate the two pseudorandom functions on the input z and add the results in the output space, or whether we first add the keys in the key space and then evaluate the pseudorandom function on z. Okay, so now for our PSA scheme. The idea is to use this key homomorphic property to construct a PSA scheme. So when we have a key k0, which is the sum of the three other keys, then this implies, by the key homomorphic property of the pseudorandom function, that when we evaluate the pseudorandom function with k0 on a label L, then this is the same as the addition of the three other POF values with the other keys on the same label L. So with this in mind, we let the trusted party perform the setup and give every party their respective secret keys, where the aggregator gets the key k0. Now, encryption simply consists of taking the client's plaintext value and adding the POF evaluation under the client's key on a label L. These ciphertexts are then sent to the aggregator. The aggregator simply adds all of them together and subtracts their own POF value. Because the blue POF value of the aggregator is the same as the sum of the POF values of the clients, they simply cancel out, and what remains is the sum of the plaintext values. Now, of course, in practice we do not do this over the integers, but we do the computations modulo a large enough public number. Okay, so next I want to explain how we can decentralize the setup and get rid of the trusted party in the beginning, and this is largely due to techniques of Chotard and others. Our goal is to create a key K0 for the aggregator, which is the sum of the 3 other client keys. And for this, the clients start by engaging in a non-interactive key exchange, which in its simplest form only consists of the clients uploading their public Diffie-Hellman key to the key server and downloading the public keys of the other clients. The clients then use these public keys of all other clients to compute a shared secret key with each other client, and then use these shared secret keys as input to a pseudo-random function to derive shared blinding terms. So now every pair of client has a shared blinding term, and in the next step we let the clients choose their PSA secret keys completely at random and encrypt them by either adding or subtracting these blinding terms. And this is done in such a way that each blinding term occurs exactly once with a positive sign and once with a negative sign. These encrypted keys are then sent to the aggregator, and the aggregator adds them all together, and because the way the blinding terms are set up, they all cancel out, and what remains is the sum of the client secret keys. And this is exactly what the aggregator's secret key is supposed to be in our PSA scheme. So now one might argue that we do not need our PSA scheme anymore because we just found a way of letting the aggregator know the sum of client supplied values. However, this method that I just described can become inefficient when the number of clients becomes large, because every pair of clients needs a pairwise blinding term. So when we have n clients, for one encryption, each client has to perform n-1 evaluations of a pseudo-random function, and therefore it is more efficient to just use this technique that I just described for the decentralized setup and afterwards use our PSA scheme, because our PSA scheme only needs one POF evaluation per encryption regardless of the number of clients. Okay, we implemented our scheme in the Go programming language, and the source code is available on GitHub. Although I should mention that we did not implement the decentralized setup, so we only implemented the standard centralized setup. For the implementation, we use a key homomorphic pseudo-random function that is based on the learning with rounding assumption and is secure in the random oracle model. The pseudo-random function is mentioned in a paper by Bonnet and others, and as ingredients we need a key from ZQ to the 2096 and a hash function h that maps from the set of possible labels also to ZQ to the 2096. The hash function then the pseudo-random function then first hashes the current label and computes the inner product of this hash value with the POF key. The result is in ZQ and then is rounded down to ZP, and in our case rounding down simply means throwing away the lower order bits of the result. Because h is required to map to ZQ to the 2096, we use multiple cores to SHA-3 to emulate this. The resulting key size of our scheme is roughly 268 kilobits, and the messages are of size of only 85 bits. In the end, we get a security of roughly 114 bits for a message space of 2 to the 64 and 1 million users. Okay, now here you see the results of our performance experiments of both our scheme and the LASS scheme of Waldner and others. On the left you see the running time of our setup algorithms, where the unit is in seconds. The running time here in green of our setup algorithm grows linearly with the number of users, because the main work consists of creating one POF secret key per user. The running time of the scheme of Waldner and others, here in blue, grows quadratically in the number of users, because for n clients, for each of the n clients, the setup algorithm has to create n secret keys. On the right you see the running time of one core to the encryption or decryption algorithm, and the unit this time is in milliseconds. As you can see in red, the running time of our encryption algorithm is constant and does not depend on the number of users, because regardless of how many users we have, encryption just consists of one evaluation of the pseudo-random function. The decryption algorithm of our scheme here in green slightly grows with the number of users, although it also only needs one POF evaluation. Apparently, adding together all ciphertexts took more time than we expected. And the running time of the encryption and decryption algorithm of the scheme of Wardner and others again grows linearly with the number of clients, because for one encryption and also for one decryption, the scheme needs n evaluations of the underlying pseudo-random function. As you can see, for small numbers of users, the scheme of Wardner and others is clearly faster than ours, although they need more evaluations of the pseudo-random function than we do. And the reason for this is that they use the AES block cipher as pseudo-random function, which is super fast, but which we cannot do because we need the key homomorphic property of the pseudo-random function, and therefore we need a POF with more structure. Okay, summarizing the talk, we proposed a private stream aggregation scheme that supports labels and is secure under adaptive corruptions. The security proof is entirely in the standard model, and when our scheme is instantiated with a pseudo-random function that is in the standard model, for example from Bonet and others, or Banerjee and Peikert, then the entire construction is secure in the standard model. Our scheme has small ciphertexts, and the encryption and decryption algorithm are quite fast, that is, for 10,000 users, under 2 milliseconds on our laptop. Limitations are that our implementation is so far only secure in the random oracle model, and it would be interesting to implement, for example, the standard model pseudo-random function of Banerjee and Peikert and see how efficient our scheme then is. The other restriction is that we still have this encrypt once restriction, and although this is also good from a security perspective to avoid this leakage that I explained with the red and the blue ciphertexts, there might be situations in which one wants to encrypt more than one message per label despite of this extra leakage. Okay, so this concludes my talk. Thank you for your attention, and I'd be happy to take your questions.